Welcome to Unit 7 of the AP Calculus Review Series. This is about differential equations, which you might be confused about because we just learned about integration. Shouldn't we be doing something like applications of integration? Well, that's the next unit. That is literally just applications of integration. This unit does have to do with integration and also derivatives. So it's just like a in-between unit before we get into some other applications. So let's get started. You might be wondering, what is a differential equation? Very good question. A differential equation is basically an equation that involves a derivative. So something like dy dx is equal to y squared minus x. That's a common differential equation. Now, we can solve some differential equations, but they have to be what is called separable. That basically means we can get all the x and dx on one side and all the y and dy on the other side. So this one is not separable because if you try to multiply by dx, you get a y and dx on the same side. But if you said something like y squared over x, it is separable because you can multiply by dx, you get dy is equal to y squared over x dx, and then you just divide both sides by y squared. That gets rid of this over here, and you have 1 over y squared dy is equal to 1 over x dx. You can separate it into two different parts. And this is exactly what the separation of variables is. It's a method to solve separable differential equations. First, you move all terms related to the independent variable on one side, all terms related to the dependent variable on the other side, just like we did here. Then you find the antiderivative of both sides and solve for the dependent variable. You basically take the integral of both sides and then solve for y. Now, that is usually going to be the end there. That is what's called the general solution. You're going to have a plus c somewhere. And we will show an example of this in our practice problems later. But sometimes there's also a particular solution, which is when they give you a point on the equation, on the function, and you can solve for c using the initial value. Sometimes it's just the general solution. You can have a constant integration. But that's differential equations in a nutshell. You might be wondering, what are we going to do with the rest of this time? There's a bunch of stuff related to differential equations that aren't exactly like core to it. It's like additional applications and things like that. First, a slope field. A slope field is basically the graph of solutions to a differential equation. You have a graph, and at each point, you plug in that value into the differential equation and plot the slope of it. So let's say it's 1, 1. You plug in 1, 1 into this differential equation. You get 1 over 1, which is 1. So you plot the slope as a little portion of the graph there. You do the same thing for a lot of different points. You plug in 2, 1, you're going to get 1/2 and 1/3 and so on. You plug in 1, 2, you're going to get 4 and so on. And then you're going to continue on like that. And you fill up the entire graph with this, and that forms a slope field. Now, at some point, you can draw possible solutions on this slope field. And all of these are possible solutions. They just kind of go with the slopes. And yeah, the entire purpose of it is that each point on the graph is the slope of the tangent line. So if you connect a bunch of the slopes, you get what the original graph would look like. But there's infinite possible solutions because of that general solution, the plus c. If you get a point on the graph, though, then you know it has to go through the certain set of slopes. There's a few key features about slope fields. If all the slopes in vertically are the same, so for example, if it's like 1 everywhere around, that means it's only dependent on the independent variable. So it would be something like dy dx is equal to 1 over x, right? It's only dependent on x. There's no y in this differential equation. But if all the slopes are the same horizontally, like this, then it's only dependent on y. Dy dx is equal to y squared, for example. Any other time, if it changes like this example over here, it's dependent on both x and y. And we can use slope fields to solve non-separable differential equations. If we had something like y minus x squared, we could plot the values and then approximate a graph based on that. Let's talk about exponential models. We're actually skipping something, but that's a BC only topic, and I'm going to save the BC only topics for the end of this video. So if you're AB, still stay with me for a second, and then after that, we're going to cut it off for BC only. Yeah, this is going to be a pretty short video. So the exponential model is basically what you might imagine. It's exponential, but we're going to talk about it in terms of differential equations. In this case, the rate of change of a certain quantity in terms of time, usually, it could be dy dx, it is usually dy dt though, is going to be proportional to the quantity itself. It's going to be equal to ky. Very simple. That's why we prefer to the regular equation, which is going to be something like y is equal to the initial value times e to the power of kt. Where this k repeats again, and then you have that constant of integration. This time we're calling it y naught, which is undeniably funny, but I did not mean it that way. Y is sub-zero. Yeah. Okay. And what can we do with this? There's something called Newton's law of cooling, and technically also Newton's law of heating, but it's usually used for cooling. It says that the temperature approaches this certain ambient temperature when it's cooling down. Let's say you put a cup of hot coffee and then you forget about it, like we all do. And the ambient temperature, the room temperature is like 70 degrees. What is going to happen is that this cup of coffee is going to cool down, exponential decay towards this ambient temperature. And the equation for that is dt dt, big T, little small t. Big T is temperature. It's going to be equal to this constant K times big T minus the ambient temperature, which is usually going to be known. And so the only variable here is this, and this is going to be a constant you solve for. And so how would you write this without differential equations? Well, temperature is equal to the initial temperature of the coffee minus the ambient temperature. This is going to be your kind of asymptote, I guess. And then e to the power of kt plus T ambient. Like I said, the T ambient is going to be your asymptote, and this makes sure that the initial value is going to be equal to T naught. And yeah, you can write this equation, you can solve for it. I would generally start with the differential equation and then work your way towards this, because they might not just like it if you just plop this equation in front of them. Same with logistic, which we're going to get into in a minute, for BC students only. But yeah, this is exponential models. And that's it for AB. Feel free to skip ahead to the practice questions. BC only students, I have a few things for you. First, while we're talking about different models, let's talk about the logistic model. This is exponential, where it's the rate of change is proportional to the quantity itself. Logistic, on the other hand, is when the rate of change is jointly proportional to both the quantity and the carrying capacity minus the quantity. So we have dy dt is equal to k, the constant of proportionality, times the quantity, times the carrying capacity m minus y, where we say m is the carrying capacity. And so if you were to solve this, we have this initial value a. So just like we had T naught here, this initial value a is going to be equal to the carrying capacity minus the initial population over the initial population. Here, we could just replace it, right? T naught minus T ambient is just valid. We can just plug it in. Instead, we could have said a equals T naught minus T ambient and done a e to the power of kt plus T ambient. That's also valid. But this we don't need an extra variable to define because it's pretty easy to plug it in. It's not so easy for logistic equations. Only when you define this can you write the actual equation that y is equal to the carrying capacity over 1 plus a e to the power of negative kmt. And now you see, if we just plugged in this value for a, it's going to look very messy. And so this is going to be your equation. Again, do not plop it just on the AP exam. Start with this and derive this equation. We will do an example of this in the practice problems. Do not worry. So you might be wondering, what are some applications of this? That is all you're going to be asked for, applications of logistic models. So first of all, the graph of a logistic model looks something like this. Right? It approaches 0 down here and some carrying capacity up here. And you've probably seen this in biology or something like that, where there's a population of like gazelles and it approaches a certain value. That's the carrying capacity. Once it goes beyond that, the population cannot sustain anymore, so it falls back a little bit until it's below the carrying capacity, at which point it can sustain it, and so it kind of oscillates back and forth. This is like an ideal logistic model, where there's no oscillation. It's just it approaches it and never goes above. That's not true in the real world, but this is our model. And so you're probably going to get a bunch of population questions, disease questions, things like that, where you're given the carrying capacity. You just need to solve for this K term and this A term and things like that. Okay, and finally, Euler's method. Technically, we were supposed to learn this before exponential models, but Euler's method is a BC-only topic, and frankly, I do not want AB to skip around a lot. I just want one entire section dedicated to BC only. So, Euler's method. So remember a few videos ago when we talked about local linearization, and I said this is going to be a prevalent theme throughout calculus, where we're trying to approximate the value of a function. Yeah, we're going to do that again using Euler's method. When I talked about local linearization, I said, well, you're using a tangent line to approximate the value of a function near that point of tangency. We're going to expand on that a bit. What we're going to do here is kind of repeated use of tangent lines. So we're going to use this tangent line here. And let's say what we want to approximate is here. As you can see, there's a very clear discrepancy between the tangent line and the function. And so we approximate a small value. And once we get the value of the function at that point, you create a new tangent line at that point. And you keep on doing that until you get something pretty close to the actual value of the function at that final point. And so this is called a step. Each iteration is a step, which is delta x. You move delta x up. So you have I iterations, right? On the ith iteration, you do f of xi plus 1 is approximately equal to f of xi plus delta x times dy dx of xi comma yi. Looks very complicated. We will do a practice problem on this. Do not worry. But all this is saying is, let's say you have a certain point. Let's say the starting point. That's the value of the function at that point. The step size, so how much you're going up. And this is the slope of the function at that point. You plug in xi and yi into the differential equation you're given. You're usually going to be given a differential equation. And the reason this works is because this is literally just the point slope form of a graph. We have y1 plus m times x minus x1, right? Just rearrange it a bit and you're going to get point slope. This y1 is just the value of the function at that point. M is just the slope, the derivative at that point. And x minus x1 is going to be that constant step size that you've been using. And so Euler's method is just point slope form multiple times. Generally, your step size is going to be relatively large, so you don't have to do too many iterations, maybe like 2 or 3 maximum. Sometimes it's a lot, though. And I think the practice problem we're going to do is a lot. So it's just to drill it into your head. And so once we plug this value in, you get the value of a function at the next point. And then you just repeat that process until you reach the final point. And that's it for our content. And we can get right on to our practice problems. Okay, both the AB and BC students now. AB students, only the first practice problem is for you. BC dominate the other two. That's because their concepts are just a bit harder. But that's neither here nor there. Okay, let's start with this first one. It's going to be a differential equation. And as you can see, it's already separable because there's only x's here. So you can just multiply both sides by dx. And you have separation of variables. And so you get dy is equal to x times cosine of x squared dx. Next step, you take the antiderivative of both sides. And so on this side is just y, but you do have that plus c1. I'm going to call it c1 for now. On this side, that looks very complicated. And finally, BC students, it's time to use, well, it's honestly, I guess integration by parts. You can use integration by parts, but it's much easier with u substitution. And I'm going to do u substitution so my AB students can also follow me. But integration by parts is a valid method here. I would not suggest using it, but if you want to practice, go ahead and try. But yeah, u substitution is just much easier because we can do u is equal to x squared, du equals 2x dx. And so if you just want x dx, that's going to be equal to half of du. And so you replace this with 1/2 du times cosine of u du, right, from before. And so this is just equal to Well, the derivative of sine is cosine, and so the antiderivative of cosine is sine. So this is just 1/2 sine of u plus c2. And we can replace that u with x squared because that is what u is equal to. I know when I say that it sounds like very bad grammar, but y plus c1 equals 1/2 sine of x squared plus c2. We have these two constants. We can just simplify them into 1. So y is equal to 1/2 sine x squared plus c. We just call it plus c. That is going to be our general solution. But we are given an initial value, so they want a particular solution. We plug in our value, we get pi is equal to 1/2 of sine of 0 squared. And the sine of 0 is 0. And so this is just going to be 0 plus c. And so c is equal to pi. And so our particular solution is y is equal to 1/2 sine of x squared plus pi. That would be our answer. Okay, and that's it for AB. That was the only practice problem for AB. BC has the other two problems. And so let's get started with our Euler method problem. This one has a step size of 0.1, and we want to calculate 0.5 starting from 0. So that's going to be 5 different steps. Ouch. That's probably going to be the most you'll ever have to do. But let's get started. Hang in with me here. We have our initial point 0, 1. We plug it into the differential equation. And that is going to be equal to 0 squared minus 1 cubed, which is just negative 1. And so the equation is going to be y is equal to negative 1 times x minus 0 plus 1. That's point slope form, which you can simplify into negative x plus 1. You plug in 0.1 into it, you get negative 0.1 plus 1, which is 0.9. Still okay numbers, but be sure to grab your calculator. It is going to get messy very fast. You plug in 0.1 comma 0.9, and you get negative 0.719. Again, I'm just using my calculator for this. I'm not showing my work because, this is just on, this should be a very quick problem for us. You would do 0.1 squared minus 0.9 cubed equals blah, blah, blah on your work. And so our equation is going to be y equals negative 0.719 times x minus 0.1 plus 0.9. Now we plug in 0.2 into this. You're going to get 0.2 minus 0.1 is 0.1. Multiply that by the slope and add 0.9. You're going to get 0.828. I have officially began rounding my numbers. I'm still going to use exact numbers in the calculations, but on the screen, I'm going to show these rounded values. So you plug in this point into the differential equation. You're going to get this equals negative 0.528. And so our tangent line is going to be that slope times x minus 0.2 plus 0.828. Plug in 0.3. You're going to get, you multiply the slope by 0.1, add 0.828. You're going to get 0.775. Plug it into the differential equation. That point that we got is equal to negative 0.376. So you can see it's going to inch closer and closer to 0, this slope. And so y is equal to negative 0.376 times x minus 0.3 plus 0.775. Okay, this is actually going to be our last iteration because after this, we're going to get the point for 0.5 and we don't have to find the slope of that or anything. Okay, plugging it into this equation for the tangent line, we have the slope times 0.1 plus 0.775, which is going to be 0.738. And so dy dx of this point is going to be equal to negative 0.241. And so our tangent line is going to be y equals negative 0.241 times x minus 0.4 plus 0.738. And so our point is 0.5. We're going to plug this into the equation. And we're going to get 0.714. And so y of 0.5 is going to be equal to 0.74 approximately. That is how you do Euler's method. This is the bare minimum of the work you should show. You should show how you got this this number by plugging it into the differential equation, and you should say how you got this number by plugging it into the tangent line, and so on. Okay, and I'm gonna have to erase the entire board to do the last problem, which is a logistic equation problem. And the reason why I can say, you can tell, is because, first of all, it's a very long word problem. And in this unit, that's usually what it's going to be, either exponential or logistic. But it says it has 200 students, and so that's going to be your carrying capacity or your maximum size. And it's a disease, which follows logistic. It doesn't exponentially grow if there's only going to be 200 students. And so it says that the disease is recognized. 2 students are diagnosed on the first day. On the 5th day, there are 12 students. Use a logistic model. Okay, literally just tells us to use a logistic model to describe the course of the equation and predict the number of infected students on day 10. So what is going to be our logistic model? Let's say P is the total number of people who are infected. dP dt is going to be equal to K times our variable P times the carrying capacity minus P. And this carrying capacity is going to be 200. And we do not know what K is. So let's go ahead and solve this differential equation. This is what you're going to have to do on the AP exam. Let's do separation of variables. We move all the P's to one side and the T's to the other. We have 1 over P times 200 minus P times dP is equal to K dt. We're leaving that K over here. And antiderivative of both sides. Okay, finally, BC students, something we can use from the last video. Partial fraction decomposition. It already gives us in its factored form. We just need to find what value of the numerator and denominator, numerator of the two expressions that makes this work. Now, it's not a particularly exciting form of partial fraction decomposition, but let's do the system of equation anyway, because I did promise you I'll show you how to do that, and we never got to do that last video. And so what we're going to do is say this is equal to 1 over P times 200 minus P. And so you multiply, you do basically common denominator, right? So A times 200 minus P plus B times P is equal to 1. And so 200A minus AP plus BP equals 1. And so B minus A basically times P plus 200A is equal to 1. What does that tell us? Well, you can replace 1 with 0p plus 1. And so b minus a is equal to 0 if that is equal to that. And 200a is equal to 1. So 200a equals 1. Okay. And so a is going to be equal to 1 over 200. B, therefore, is also going to be equal to 1 over 200 to make the first equation true. Okay, that was nice. I'm also going to have to clear it now to have enough space for a logistic model. And so this is going to be equal to 1 over 200p plus 1 over 200 times 200 minus p. Or, if you're smart, you would just factor out the 1 over 200 because that is both of them. And you would get 1 over p plus 1 over 200 minus p dp. It's going to be integral of 1 over p dp plus integral of 1 over 200 minus p dp. And that is going to be equal to, well, that's just ln of p, absolute value of p, minus ln of 200 minus p plus c. Don't forget the 1 over 200 in the front, though. And so I'm going to bring it back. But first, properties of logarithms, we can do ln of absolute value of p over 200 minus p. And so we also know that the population will always be constant, will always be positive. So we don't need the absolute value. We add the 1 over 200 in the front, and this is, let's say, plus c1. And the other side, though, will be k integral of k. That's just going to be kt, and then plus c2. And so we multiply both sides by 200. We get ln of p over 200 minus p is equal to kt plus c. Well, 200 kt plus c. And we can take both sides to the power of e. So p over 200 minus p is equal to e to the power of 200 kt plus c. And this e to the power of c is also just a constant. And so we can get rid of that exponent and just add the constant as a coefficient. We're going to use a instead because that's what appears in the logistic model equation. What next? How are we going to solve for p? Well, let's try getting all the p's on one side, which we did, but we wanted there to be only one p, not a fraction of p. So P is equal to AE to the power of 200 KT times 200 minus P. And so we can we can use distributive property. So 200 AE to the power of 200 KT minus AE to the power of 200 KT P. And this looks very complicated. So we have to be very careful here. We add this expression to both sides and we get P plus that, which we can factor out a P of. And so we write P times 1 plus AE to the power of 200 KT is equal to 200 AE to the power of 200 KT. Now we divide by this expression that we have. So P is equal to 200 AE to the power of 200 KT over, we have 1 plus AE to the power of 200 KT. This doesn't look like what we promised at first, but that's because we have 2 AE to the power of 200 KT. We can simplify it a bit by multiplying the top and bottom by AE to the power of negative 200 KT. And so what that would do is that would basically cancel out all the exponents over here. All we're left with is 200 in the numerator. In the denominator, that would cancel off with this 1, and it would multiply this 1 by that. And so when we simplify, we're going to just have, well, when we do this exponent by the one we're multiplying by, it's just going to cancel off to 1, and then we now have an extra copy of the exponent with a negative in it. And so what it would look like is this. We have that 200 in the numerator, and then we have that 1, which cancels off the exponents, plus AE to the power of negative 200 KT. And now we have our equation. We just need to solve for A and K. In this case, we have two points. We know that on day 0, it's 2, and on day 5, it's 12. So you plug in 0 into here. Well, now the K doesn't really matter. We get e to the power of 0, which is 1. And so 200 over 1 plus A is equal to 2. And so A is going to be equal to 198. That's good to know. We can replace A with 198. Or sorry, A is not going to be 198. My apologies, I did subtraction instead of division. So 1 plus A is going to be 100, and so A is equal to 99. And now we have to solve for K. How are we going to do that? We use the other point, which is 5, 12. You plug in 5, you plug in 12. That's going to be pretty complicated. So we do 12 divided by 200 is equal to 1 over 1 plus 99 e to the power of negative. 200 times 5 is 1,000. 1,000 K. We're going to get a very weird decimal. So first, 12 over 200 gives us 0.06. We have to do 1 over that to get this expression in the numerator. Then once we get that, which is 16.667, we subtract 1, divide by 99. That is going to get us, again, a very weird number. We're going to get 0.158. And that's going to be equal to e to the power of negative 1,000 K. Okay, what do we do from there? We take the ln of both sides. We're going to get a negative answer as expected. So now negative 1,000 K is equal to negative 1.844. And now we divide, first we get rid of the negative by multiplying by negative 1. Then we divide by 1,000 to solve for K. And eventually we're going to get a value of K that is K equals 0.00184. And now we can plug that in the numerator, or as the exponent of the denominator. We multiply by 200. We're going to get 0.369. And so, erasing all this, this exponent is going to be negative 0.369 times t. And that would be our equation for the number of students infected on day t. That's not it though. They want us to predict the number of students infected on day 10. So we just plug in 10 into t. We have 200 plus 1 over 1 plus 99 times e to the power of negative 0.369 times 10. We're going to get p of 10 is approximately 57. Well, we can not really have a fraction of students, so we just round to 57 students. That would be your answer. And yeah, that's it for this unit. It seemed like it would be short at first, but we did have two hard problems to do for BC students at least that do take some time. Euler's method and a logistic model. And so while the content review was not that much, the practice problems were. And so I'll see you next time in Unit 8, which is, once again, applications of integration.